Alright, welcome back guys. So today we're going to cover 6.2, in which we're still going to be finding confidence intervals for the mean. However, the standard deviation for the population is not going to be given. And this is more realistic, right? Because if you're trying to create a confidence interval for the mean and you actually know what the population standard deviation is, then you should know what the population mean is. So this is more realistic here. So we're not going to know the standard deviation of the population, and because of that we're going to rely on the standard deviation of the sample. Okay. That's going to be sort of another point estimate in a sense. All right, let's look at these learning objectives. So we're going to interpret the t-distribution and use a t-distribution table. I will show you a t-distribution table, but we're really not going to be using it. And then secondly, we're going to actually construct and interpret confidence intervals for a population mean whenever sigma is not known. Okay, so this is pretty much just like what we did in 6.1, guys. However, the only difference is we don't actually know the standard deviation of the population. So we're going to use the standard deviation of the sample. And so the way we do this is we define this other random variable. Okay, we call it t. And it is defined to be x bar, so the sample mean minus whatever the population mean is, divided by the sample standard deviation over the square root of n. Okay, so a couple of things we've got involved here. We've got, instead of sigma, we've got s involved, so that's the standard deviation for the sample. And furthermore, we've got the square root of n involved again. Okay. And this new variable follows what's called a t-distribution. And we're going to talk a little bit more about that. A t-distribution, guys, is very similar to a standard normal distribution. It's a bell-shaped distribution. It's just that the tails on it can be a lot thicker depending on how large or small the sample size is. And you can sort of think of it this way: since we don't know what the population standard deviation is, then there's more uncertainty in the mix, and therefore we're going to use a wider, thicker distribution, okay, when we're creating these confidence intervals, because there's more uncertainty at play. We're having to use the standard deviation of the sample to estimate the standard deviation of the population. And we're also using, of course, x bar is our estimator of the population mean. So anyway, like I was saying, the tails in the t-distribution are thicker, okay? And then the standard deviation of this t-distribution is going to vary depending on the sample size. And this goes back to what I was talking about last class. As the size of your sample increases, so too does the certainty or the reliability of your point estimate, okay? And we're going to see that today. In fact, if you look, well, let me read this last bullet point. It says the t-distribution gives us a way to calculate a confidence interval for a population mean when sigma is unknown, okay? And we're going to be using what's called a number of degrees of freedom. And really this relies on, what this is, guys, is essentially the certainty that's related to the size of our sample. Okay, so the t-distribution is not a single curve, but actually a family of curves. Okay, they're all symmetric, they're all bell-shaped. But how, I guess, horizontally compressed or stretched they are depends on the sample size, or in other words, depends on the number of degrees of freedom. Okay? And if you look down here, the degrees of freedom is defined to be 1 less than the sample size. So look at these three different t-curves, or three different t-distributions that we have right here. Well, no, this is only 2, and then the standard normal curve is in turquoise here. So see how it's much tighter than the other 2 curves? This curve right here in gray, this is the t-distribution with 5 degrees of freedom, or in other words, when the sample size is 6. And then this distribution here in black, this is a t-distribution whenever the number of degrees of freedom is 2, or in other words, the sample size is 3. So notice, as the sample size gets smaller, the distribution gets wider and it gets thicker in the tails, and that's because the smaller the sample size, the more uncertainty, right? And as we increase the sample size, then that t-distribution becomes narrower because we're becoming more certain, okay, about our point estimator, or the accuracy of our point estimate. But anyway, so similar to how we did in section 7.1, we had to find the critical z-score, we're going to be finding a critical t-value, okay? And so this will not only depend on the level of confidence that we want, but also on the sample size, or in other words, the number of degrees of freedom. Because the sample, each t-distribution that corresponds to each size of sample is its own distribution. So to find the actual critical t-value, we have to know the number of degrees of freedom, okay, to define that's one specific distribution, and then subsequently find those particular critical t-scores. All right, so similar to what I was saying, it says finding confidence intervals using the t-distribution is going to be exactly like what we did in 6.1, using the standard normal distribution, except instead of using a critical z-score for our critical values, we're going to be using a critical t-score. And again, that's because we are not using the standard normal distribution, we are using the t-distribution, okay? All right, and the first thing we're going to do, similar to what we did in 6.1, is just get some practice finding those critical t-scores. So example 1 here, it says, find the critical t-value, t sub c, for a 95% confidence level that has a sample size of 15, okay? So to find these, in this case, we need both of these. We need not only the confidence interval, but also the size of the sample, because we need to first calculate our number of degrees of freedom, which in this case, 15 minus 1 is 14. And knowing that defines the particular t-distribution, okay? And then lots of times, as always, guys, it's helpful to draw a picture. So we're trying to figure out, you can find either the leftmost or the rightmost, okay? Because these values are symmetric, just like those critical z-scores under the standard normal distribution. So if we have 95% of our distribution in the middle, that means we have the other 5% in the tails, or in other words, we have 2.5% in each tail. And so, just like we did in finding those critical z-scores, we can use the calculator again. There's another feature. Instead of inverse z, it's called inverse t. And what you do with it is you need to know the level of confidence. You need to know the area to the left, okay? And furthermore, you need to know the number of degrees of freedom. And it says when you're prompted, you're going to input the area to the left of the curve. So for this particular example, they're trying to find this upper value. So you've got 95% right here, and then you've got this other 2.5%, okay? So you've got 97.5% to the left. So you can find it that way, or you can just try to find this negative value and make it a positive. Okay? So that's probably the way that I will actually do it. But anyway, let me show you this. Okay, so you're going to come over here to stat. No, actually you're going to go to distributions, I'm sorry. And it's not inverse normal anymore. It's inverse t, okay? And so when you hit this, it's asking for the area to the left of the curve, which is 2.5%, okay? And then it's asking, secondly, here for the number of degrees of freedom, which in this case is 14. And then you can paste this in there, and it will, sometimes it takes it a second, it'll calculate that value. So you can see it's negative 2.145. Okay, if I go to negative 2.145, but remember, we want the positive value because that's what we're going to be using to find that margin of error in our margin of error calculations. Oh, also, let me show you how you could do this using the table. So there's a table at the back of your book. What you would do is you would just look up here. This top row lists the different levels of confidence. So we're interested in a 95, being 95% confident. And then you just scroll down here to where the cell matches over here with the number of degrees of freedom. So we have 14 degrees of freedom, so that's going to correspond to this value right here. So 2.145. Okay. And guys, I want to point out that these critical z-scores, they're going to be farther away. They're not going to be as close as those critical z-scores. And the reason is because the t-distribution is more varied. It has more variance in it because of that uncertainty from not knowing the population standard deviation. So you can think of it as being like a wider, looser distribution. All right. And if you had put in the area to the left of that upper z-score, you would have gotten the same thing, okay? Either positive or negative 2.145. All right, so let's get a little practice doing this. So it says find the critical t-score for the confidence level of 99% with a sample size of 27. All right, well, I might show you one last time how we could use the table. Okay, so it's a 99% confidence interval that we'd be interested in. So we're in this last rightmost column here. So I'm going to scroll down to where we've got 27 degrees of freedom. So you can see right here it's 2.771. So I'm going to say T of 0.99, because that's our level of confidence, equals 2.7, oh, I forgot. That's what I thought, 2.771. Just thinking there were two sevens. There we go. And then, if you want to use your calculator, the calculator is probably what I'll use from here on out. You just go to distributions, go down to the inverse t function. Now, well, I guess this is one downside of using the calculator. You've got to figure out the area to the left, okay? So the area to the left, if you have 99%, that leaves another 1% in the two tails. So that means in only one tail you're going to have 0.5%, or in other words 0.005. Okay, so that would be the area to the left. So really all I'm doing here is I'm saying 1 minus the area between the two z-scores, which is 0.01, and I'm just dividing that by 2. And that's how I get this area to the left. Okay. All right, so I'll type that in. And the number of degrees of freedom is 27. Hit enter. And it takes this one a minute. You can see, rounded to 3 decimal places, it is well, this is one's negative, of course, but you would change it to a positive 2.771. Okay. So that would be that critical z value, or critical z-score. All right, number 3, find the critical value, T sub c, for the confidence level of 90% and a sample size of 19. Okay, so if I have 90% in between those two T scores, and that means I have 10% in the two tails, which half of 10% is 5%. So if I'm using my calculator, I'm going to have 5% of the distribution to the left, so 0.05. And then the number of degrees of freedom here is 19. Okay. All right, so to 3 decimal places, we'll just call this a 1.729. Okay, so z of 90% is 1.729. Yeah, so I wrote z there, didn't I? Instead of t. Yeah, so if you compare these t values with their corresponding z values, you'll see that they're actually further away. They're farther out, away from the mean, okay? And then I'll show you this one real quick in the table as well. It was a 90% confidence interval, and there were, I believe, 19 degrees of freedom, and here we are right here, okay? 19 degrees of freedom, 1.1729. All right, and then, well, let's see. Oh yeah, let's go ahead and do this one. It says find the critical value, T sub c, for the confidence level of 95% and a sample size of only 2. So my guess here is that this t value is going to be even further from the mean, okay? Because a sample size of 2, guys, is not very robust. It's not going to tell you much about the population. It's so small. And so a t distribution that corresponds to n equals 2 is going to be very wide. Okay, yeah. Okay, so if there's 95% in between the two t values, there would be 2.5% to the left of the lower t score. So I'll use my inverse t function again, and I'll have 2.5%. And there's only 2 degrees of freedom. Wow, this one is, we'll take the absolute value of this, so it'll be 4.303. So t of 0.95 is 4.303. So that is pretty far from the mean, okay? If you remember from 6.1, the corresponding z-score is 1.96. So this is much farther. And that's because there's a lot more variation in the t distribution when there's only 1 degree of freedom. 1 degree of freedom. Is that what I put? No, actually I put 2 in there. The sample size is 2, so the number of degrees of freedom is just 1. So yeah, be careful here. Let me go replace that 1 with 2. So now this value is going to be even farther. Oops. Ooh, yeah, look at that. That's really far. So negative 12.706. That's pretty shocking. 12.706. Remember, we just want the absolute value of it. So that is very far from the mean. And when you consider, like I mentioned a second ago, the corresponding z-score would be 1.96. And that's because this sample size is so tiny that you can't really even make any inferences to the actual population with a sample size that small. Guys, lots of times you'll hear people refer to that parameter n. They'll say, when I listen to podcasts and things, if they're talking about a research study or a specific study, they'll say n of, and they'll give it value. So if n is typically, 10 or 15, that's not a very robust study. And you can't have a whole lot of faith in the results of a study in which the sample size is so small. You really want a large sample size to give you the most accurate picture of what the population is like. All right. Okay, well, let's go on to actually constructing some of these intervals. Well, we know how to find the sample mean, okay, in case we ever had to do that. And we know how to find the sample standard deviation. I showed you guys this way back in 2.4. However, that was something we didn't do by hand, right? Because of the tedium involved. You just find the individual deviations, you square each one, you sum them all up, and then you divide by n minus 1 and take the square root of it. All right, you also need to identify the degrees of freedom. This will be based on the sample size. You need to know your confidence level, as always. And you need to find your critical t-values. And once you know that, you can find your margin of error. So think back to last class. The margin of error, whenever we knew the standard deviation for the population was z sub c times sigma over the square root of n, okay? So the only two things that are different is we're using t sub c and we're using the sample standard deviation, okay? And once you know what that margin of error is, you just subtract it and add it to find your left and your right endpoint for your confidence interval, okay? You subtract it from the mean, and then you add it to the sample mean, and that will give you a range. That'll give you that specific confidence interval associated with that specific level of confidence and that specific number of degrees of freedom. As the number of degrees of freedom increase, that would be a result of the sample size being larger, okay? Then your confidence interval will get narrower, because this value right here, since n is in the numerator, this whole quantity right here will actually become smaller. Your margin of error gets smaller, okay? Which makes sense because you can be more certain because you're utilizing a larger sample. It's giving you a better picture of the population. But anyway, let's do, well, first we're going to kind of segue into this. The first thing we're going to do is actually calculate a margin of error, and then down here we'll look at finding some actual confidence intervals, okay? All right, well, number 5 says find the margin of error for the given values of C, S, and N. So I'm going to recopy this formula right here so we've got it to reference, okay? All right, so C is 98%. So we need to find the critical t-score associated with a 98% level of confidence. Well, if there's 98% in the middle, that means there's 2% in the two tails, and that would leave 1% in just one tail. Okay, so I'm going to get my inverse normal function, and the area to the left of that lower t-score would be 1%. Whoops, I went into the inverse normal, didn't I? Here we go. Oh, well, I'm still in that. I need to just quit this screen. here we are. So 1% to the left. And then because the sample size is 18, that means we're going to have 17 degrees of freedom. And that's it. So let's round this to 3 decimal places, 2.567. So it'll be 2.567. That's our critical t-score. So the error, or the margin of error, will be that critical t-score times the sample standard deviation, which is 6, divided by the square root of the sample size, so square root of 18. You can put all this in your calculator if you want. Guys, if I want to reuse this number and change its sign, I can just multiply it by -1. And then I can say times 6 divided by the square root of 18. Okay? Hit enter. And there we go. That's the margin of error. I'm going to round this to 2 decimal places, so 3.63. And the margin of error is also going to be bigger as well when we don't know the population standard deviation. Okay. So, you know, if S had been sigma, this margin of error would be smaller. All right, well now let's actually construct one. So we know how to find the margin of error. Once you find it, you just both add it and subtract it from the mean to find your lower bound and the upper bound of your confidence interval. So that's what I'm going to do with number 6 here. Construct a confidence interval for the population mean, mu, using the t-distribution. Assume the population is normally distributed and C is 95%. Of course, it gives us the sample mean, gives us the sample standard deviation and the sample size. Okay, so I'll do this one manually. I need to find T of 0.95. So if there's 95% of the area in between those two t-scores, I would have 2.5% of the area to the left of the leftmost t-score. So I'm going to come back to my inverse t function and type in here 0.025 of the area to the left. And now we've only got 9 degrees of freedom. 1 less than 10 is 9. Okay, so we get 2.262. Okay. So I'm going to find my margin of error. Come up here so we can see that. Reference that formula. So our critical t-score times the standard deviation divided by the square root of 10. And I'm going to do this one like that last one. Just multiply by -1 to turn that z-score or t-score into a positive, and then I'll multiply it by 2. And divide, well, I didn't actually hit the multiplication key, did I? Multiply it by 2, and then divide by the square root of 10. Oops, got an issue with my syntax. Oh, well. Well, let's just see what this is, and then I'll multiply it by the 2.262. Alright, so we get a margin of error. I'm going to go to 2 decimal places, so 1.43. Okay. Alright, so to find my interval, guys, my lower bound will be x bar minus the margin of error, and then my upper bound will be x bar plus the margin of error. Okay? So essentially, if x bar is 14.1, and I subtract the margin of error, you get there's sort of an argument to be made here that I should have just rounded this to 1 decimal place, because we only know this to an accuracy of 1 decimal place. But I'll just leave it like this, I suppose. And then 14.1 plus that margin of error. Okay, so you would just calculate those two. 14.1 minus 1.43. Now this, I will round to the nearest tenths. I'll say, I'm going to, well, no, I'll leave it like that. 12.67. This has to do with something you guys may have studied before, significant figures or significant digits. You know, my answer here can only be as accurate as my least accurate number that was involved in the calculation. So that's why. All right, I get 15.53. Okay. And I would, at the end of this, guys, since the mean is just given to the nearest tenths place, I'd probably just round each of these to the nearest tenths place. In fact, I'm just going to do that. I'm going to say this confidence interval goes from 12.7 all the way to 15.5. Okay. All right, now that's how to do it by hand. So it's just like finding those confidence intervals by hand in 6.1. However, guys, again, there is a function in the calculator that will calculate these t intervals for us. And I'll show you that right now, I guess. So you're going to come to Stat. You're going to go to the right over to Tests. And you're going to scroll down, not to number 7, that's Z interval. That's what we used in 6.1. We're going to go down here to T interval. And it'll ask us, we're using the statistics, not the actual data. It'll ask us for X bar, which is 14.1. This is the sample standard deviation, okay? And it is 2.0. It'll ask us for the sample size. It does this in order to calculate the number of degrees of freedom, and then we'll put in the level of confidence that we want, 0.95, okay? All right, so I calculate it, and you can see I'm real close, aren't I? 16.7 and 15.5, that's what these would round to. Okay, so from here on out, I'm just going to use the calculator. Save me from having to do all this arithmetic. All right, well, number 7. Use the given confidence interval to find the margin of error and the sample mean. Okay, so in this case, we're already given the confidence interval. It's going from 15.4 all the way to 22.2. We want to find what the actual sample mean was and what the margin of error was. Well, remember, the sample mean is right in the middle of this. So I'm really just trying to find the midpoint. So all I need to do is average those two numbers, or average those two bounds, 15.4 plus 22.2, divide that by 2, and that will give us 18.8. So that is what X bar is. That's the middle of this interval. And then once you know that, to find the margin of error, you can just simply take either one of these. I'll take the larger bound and subtract from it the actual mean. We just need to know what that distance is. Or if you wanted to use the lower bound, you would take the mean and subtract from it this lower bound, and that would give you the margin of error. But well, I've already got 18.8 in here. I think I may just do that. Subtract from it the 15.4. So 3.4. And that's what you would get right here as well. So the margin of error is 3.4, okay? All right. All right, well, let's look at, I think I'm just going to do one video here again, guys, because we've got this chart at the very end. So we really just have 3 more examples here. All right. Number 8, it says in a random sample of 27 people, the mean commute time to work was 34.8 minutes, and the standard deviation was 7.1. Okay, so these are the statistics from the sample. This is X bar, and this is S. Assume the population is normally distributed and use a t-distribution to construct a 98% confidence interval for the population mean. And what is the margin of error? Okay. I hate that it asked that last part. Actually, we already know how to do that, guys. I think I'll just skip it, if that's okay with you. Okay, but I need to start off by finding that critical t-value. So again, if we've got 98% of the area between our 2 critical t-scores, that leaves 1% in each of the tails. Okay, so if I use my inverse normal, my inverse t function, the area to the left of that lower t-score would just be 1%, or 0.01. And then in this case, this consists of 27 people, so our number of degrees of freedom. Wait a minute, why am I doing this? I guess because I was thinking we were going to actually find the margin of error. We don't need to do this, guys. If all we're trying to do is construct the confidence interval. Oops, didn't mean to do that. All we need to do, so we can use our calculator. We can go to the t-interval. Okay, if you remember, you come over here to stat, go over to tests, go down to number 8 for t-interval. This saves us a lot of work. Okay, all right, well, X bar is 34.8, and then S is 7.1. So we'll put these statistics in here. 34.8. The sample standard deviation is 7.1. The size of the sample is 27, and the level of confidence is 0.98. Okay, and this will construct our interval for us, so we don't even have to worry about finding a critical t-score. All right, so I'm just going to go to 2 decimal places. 31.41 would be our lower bound, and then 38.19 would be our upper bound. Okay, now technically the units are important. This would be in minutes. Okay, so the mean commute time, the true mean commute time for the population, 95% of the time, or no, 98% of the time, if we take a sample of this size of people, it should fall within this interval. Okay, so we can say in a sense that we're 98% confident that the true commute time, or average commute time, is within this interval right here. Okay. Alright, well, let's try number 9. These are really all the same, guys. Here it says in a random sample of 5 mobile devices, so in here is going to be 5. The mean repair cost was $90, so that is X bar, and the standard deviation was $11, so that's S. Again, we're assuming a normally distributed population, and that has to be true in order for you to be able to use the t-distribution. and use a t-distribution to find the margin of error and construct a 99% confidence interval for the population mean. Okay. For this one, guys, I will go ahead and find the margin of error just because I think your homework is going to ask you, and I only have one previous example. So what I need to do is find a critical t-score that corresponds to 99%. All right, so that means there would be 1% in the tails, or in other words, a 0.5% in the leftmost tail. So if I go to my inverse t function, the area to the left would be 0.005. That's 0.5%. And the degrees of freedom would be 5. Or no, it would be 4, wouldn't it? I keep forgetting to subtract 1. Okay, so this is it. Let's go to 3 decimal places. -4, or just 4 rather, 4.604. Okay. And then to find the margin of error, you take your critical t-score, you multiply it by S, which is $11, divided by the square root of the sample size, which is 5. Okay, I'm just using that formula. And let's calculate this. So I'm just going to multiply this by -1 to turn it positive. And I'm going to multiply it by 11 divided by the square root of 5. And we get, this is a big margin of error. Let's round this to 2 decimal places. 22.65. Technically this would be in dollars. Okay. This is a really large margin of error. And the reason is because the confidence interval is really high. So the higher the confidence interval, the wider, the higher the level of confidence, the wider the confidence interval. And furthermore, because this is such a small sample size, that's one of the reasons this margin of error is so large. And then if you manually wanted to find the confidence interval, you would just take this value, both subtract it and add it to the mean right here, okay? But I'm going to use the calculator again. I'm going to go to Stat, go over to Tests, down to t-interval. Oops. So the average is $90. The sample standard deviation is exactly $11, but the sample size is only 5. And then our confidence level is 99%. Alright, so this is going to run from $67.35 on the lower end all the way to $112.65 for our upper bound. Okay, so that's it. That's the confidence interval, and that's what you would have got if you had both added and subtracted this margin of error from the mean. All right, well, the last one here, guys, we are actually using the data itself. So it says the state test scores for 12 randomly selected high school seniors are shown below. Okay, and then it asks us to find the sample mean, the sample standard deviation, and then construct a 95% confidence interval. Well, you can do all this in your calculator. Okay, that's what I'm going to do. I'm going to input this. I'm going to come over here to Stat. I'm going to edit a list. And it's going to be list 1. I'm going to input this data. 548, 630, 1,441, and 944. You got to be careful. You don't one improperly input data value, and my results are, erroneous. All right, now I'm going to come back over here to stat. I'm going to go to tests. I'm going to come down here to t-interval. But now we're not using the statistics from this sample because we don't know what they are. So I will come over here and click enter on data. So what the calculator will do is it will calculate the mean and the standard deviation of this sample, and it'll use those in calculating this confidence interval. Okay. I've got my data in list 1. Frequency, you're always going to keep it 1. And then my level of confidence, I want a 95%, so 0.95. Now you just hit calculate. Okay, so we get a lower bound of 717.91. And we get an upper bound of 1,103.6. And fortunately for us guys, look what it does. Calculator will go ahead and list the sample mean and the sample standard deviation. See, so I saved myself a lot of work. So the sample mean is 910.75, and then the sample standard deviation is 303.5. Okay, and that's it. And that is the last one, guys. So in many respects, this is very similar to finding those z intervals in 6.1. The last thing right here that I have is an actual chart, a flow chart. And this actually tells you when to use which distribution when calculating confidence interval. It says, is the population normally distributed, or is n greater than or equal to 30? If either of these cases is true, then you've got two options. Well, yeah, if either of these cases is true, then you have two choices. Is sigma known? Yes or no. If it is known, you're going to use the standard distribution, standard normal distribution. If it's not known, then you use the t-distribution with S, the standard deviation from the sample. If neither of these conditions had been true, then we cannot use either of those distributions to construct a confidence interval. Okay. I don't know that you're actually going to need this, but I put this in here in any case. All right, and then I'll see you in 6.3, in which we will still be constructing confidence intervals, but we'll be constructing confidence intervals for a proportion. And this is where you find this in any sort of polling, like presidential polling or things of that nature, when you're talking about a percentage. What's the true percentage in some population? Okay, then you have to use confidence interval for a proportion. Or in other words, what proportion of the population supports X candidate? So anyway, I'll see you in 6.3, guys.